Welcome to video 1 of part 2 of chapter 6. More about the standard deviation as a ruler in the normal model. Last time we talked about the 68, 95, 99.7 rule, and that's great when everything's exactly 1, 2, or 3 standard deviations away from the mean. But when a data value doesn't fall exactly 1, 2, or 3 standard deviations from the mean, we can look it up in a table of normal percentiles. We can also use technology like our CASs to find these things out, and we're going to go over both methods. Table Z in Appendix D provides us with normal percentiles, but many calculators and statistics computer packages provide these as well. Also, if you take the equation, the formula, the function that models the normal curve, you can find the area underneath the normal curve using calculus. But this is a non-calculus based course, so no worries. We'll use either tables or technology. Table Z is the standard normal table. We have to convert our data to z-scores before using the table. The figure shows us how to find an area to the left when we have a z-score of 180. So it's the area to the left of 1.80. So that is also corresponds to the idea of the probability of getting a z-score less than 1.80 and the percent of observations that will have a z-score less than or equal to 1.80. So you look in the first column, and you'll notice that it has a bunch of numbers rounded to the nearest tenth. And then if you look across the top row, it has 0.00, 0.01, 0.02, all the way to 0.09. So what you do is you look for the correct row by finding the ones and tenths place that you need, so 1.8, and then you go over to the column with the correct hundredths place. So since we want 1.80, we look in the 1.8 row, the 0.00 column, and we get 0.9641. So I just should grab your book and see that it's the same entry in your book. Okay, so that means the area to the left of 1.80 and under the standard normal curve is 0.9641. The area underneath the whole curve is 1, so this is almost the whole area. The areas in the table are always to the areas to the left of a particular z-score. This also means that 96.41% of all observations in the standard normal distribution, all z-values would be less than or equal to 1.80. It also means that the proportion of observations would be 0.96. The probability of having an observation that has a z-score 1.8 or less is 0.96. All those things are synonymous. Many calculators and statistics programs have the ability to find normal percentiles for us, and we will find normal percentiles with your CAS later in this presentation. Sometimes we start with areas and need to find the corresponding z-score or even the original data value. For example, what z-score represents the first quartile in a normal model, where the first quartile is the cutoff point for the lowest 25%. So the area to the left of the first quartile is going to be 0.25 or 25% of that area of 1. Look in Table Z for an area of 0.2500. The exact area is not there, but 0.2514 is pretty close. Okay, in fact, it's the one that's the closest to 0.2500. So you look for the entry that is the closest, whether it's above or below, to the entry you're looking for. And then you look and you get the hundredths place by what column it's in, and you get the ones in the tenths place by what row it's in. So since 0.2514, and look, actually use Table Z and look at it, you can see that the row is the negative 0.6 and the column is 0.07. So the figure is associated with z equals negative 0.67. So the first quartile is 0.67 standard deviations below the mean. Okay, are you normal? How can you tell? When you actually have your own data, you must check to see whether a normal model is reasonable. Looking at a histogram or dot plot or stem and leaf diagram of the data is a good way to check that the underlying distribution is roughly unimodal and symmetric. A more specialized graphical display that can help you decide whether a normal model is appropriate is the normal probability plot. If the distribution of the data is roughly normal, the normal probability plot approximates a diagonal straight line. Deviations from a straight line indicate that the distribution is not normal. This is one of your options on the CAS. Whenever you do a plot, when you're choosing plot types, you can choose a normal probability plot. So nearly normal. The data have a histogram and a normal probability plot that looks somewhat like this example. Now they've got the histogram, oriented a different way than we usually do. But if you kind of turn your head, you can see, all right, it's unimodal and symmetric. The normal probability plot, the scores are lining up on fairly well on a diagonal line, so that indicates normality, or at least not exact normality, but approximate normality, or nearly normal. A skewed distribution might have a histogram and a normal probability plot like this. So again, I guess they're trying to show you the association between the histogram and the normal probability plot. I'm not really worried about that, but clearly that histogram is skewed to the right, to the larger values there to the right. Remember the trail of the tail tells where the skew is, and so since the tail is trailing to the right, it's skewed to the right. And you can see that the normal probability plot, there's a big old curve and a wiggle in it, and so that indicates that our distribution is not normal. So what can go wrong? Don't use a normal model when the distribution is not unimodal and symmetric. Don't use the mean and standard deviation when outliers are present. The mean and standard deviation can both be distorted by outliers. Remember, they are non-resistant measures. Don't round off too soon. Don't round your results in the middle of a calculation. Wait to the end to round. Don't worry about teeny tiny minor differences in the results, like in, the thousandths place and that sort of thing. The stored data can tell may be easier to understand after shifting or rescaling the data. Keep that in mind. Shifting data by adding or subtracting the same amount from each value affects measures of center and position, but not measures of spread. And rescaling data by multiplying or dividing every value by a constant changes all the summary statistics, center, position, and spread. And we talked about that more last time whenever we were talking about the just coming up with the z-scores. We've learned the power of standardizing data. Standardizing uses the standard deviation as a ruler to measure distance from the mean, and that gives us z-scores. And so the z-scores tell us how many standard deviations above or below the mean a particular observation lies. With z-scores, we can compare values from different distributions or values based on different units. Z-scores can identify unusual or surprising values among data. Okay, but anytime you have a z-score of like 4, you know that that's huge compared to the mean. So even if it's you're looking at data and you don't have a real good familiarity with the units that are involved or even the items that are involved, if you get a z-score of 4, you know that observation is large, especially if they're normally distributed. We see the importance of thinking about whether a method will work. We check the normality assumption, or we hold that assumption. We sometimes work with normal tables, table Z. These tables are based on the normal model, and in our examples, we're going to see how to use our CAS to do the same thing. Data can't be exactly normal, so we check the nearly normal condition by making a histogram or dot plot or stem and leaf diagram, and we ask, is it unimodal, symmetric, and free of outliers? We can also use normal probability plot, and there we ask, is it straight enough? Okay, let's look at some examples. What percent of a standard normal model is found in each region? We're going to draw a picture and we're going to answer that. But you know what? I think this is probably a good time to do a break in the video. So we're going to come back and begin our practice and begin our examples with video 2.